Hello students, today I will continue the tutorial on using the MNE toolbox for analyzing EEG or MEG data. So in the previous class, we have seen how we can load the data into an MNE environment, how we can perform some basic pre-processing, such as removing the eye blink related artifact using ICA, or performing some segmentation. I will show you different ways that we can use MNE to visualize the data. This will be very helpful to reproduce all those figures of the graphs that we have covered in the lecture. It is also important to gain some insight in the data for exploratory data analysis, visual inspection of the EEG data, and possibly using or generating high quality figures for your reports. Today I will be using the Jupyter Lab IDE for demonstrating all those visualizations. Let me first load the data that we have segmented from the previous class, right? So first import MNE and matplotlib, and the file name is as follows. So oddball-epo.fiv is our segmented ERP dataset. We're going to be using the MNE read epochs method to load this data. Okay, so let's take a look how it looks like. Let me create epoch. Okay, info. This is information field. And just epochs from the previous class consist of standard and then target ERPs. So the standard is non-target ERP, target ERP, where total number of trials are equal to 106 after equalizing. And we have the following duration segmented: 200 milliseconds pre-stimulus and 500 milliseconds after the stimulus or after the stimuli. We can take a look at epochs get data, some of the examples of NumPy array. Okay, so this is our dataset by array. So after performing segmentation, what is the next step? Okay, what we can, because we have two different conditions, the first step in the analysis of ERP is to visualize, to visually inspect. So for that, we can first perform averaging across target and then non-target ERPs. So the MNE has the method called averaging, okay, which performs as averaging across all target examples. And let's call the non-target as standard. The next step would be to visualize these average, target, and non-target or standard ERPs. Let's first quickly compare the NumPy array dimensionality before and after averaging. So here target and standard corresponds to the averaged ERPs from 106 trials each. Epochs get data, shape. This is the dimensionality of the all data, including target and standard ERPs. Let's get epochs, target, get data, shape. This is our NumPy array shape. So with 106 trials, 63 channels plus stimulus channel, and then 71 time points. Now let's take a look at the average target dimensionality. So the dimensionality of the average target ERP is as follows: 63 channel and time points across 106 trials, right? So target info should provide us information about this object. So all these EEG channels, 63 channels, okay? And if you want to see all the names of the channels, you can target.info and then type channel names, which will show all the channel names. Now next step is to explore the visualization capabilities of the MNE. So for that we call our dir function and then target, just to check what kind of plot function we have here. We usually look for these functions. So plot field, plot image, plot joint, topo map, sensors topo, and some other information. So we're interested in these methods. Okay. So let's pick some of them. Okay, and then explore. Let me just copy paste for reference. No, okay. Now first step is, let's try to see the plot method, okay, and then just try to plot the average ERP. This is averaged ERP from 106 trials, target ERP. You can see here we can see a prominent evolution of the P300 waveform from 0.2 seconds to 200 milliseconds and up to 400 milliseconds. We can also check other methods or functions. For example, target plot topo map allows us to visualize this topographic map of this ERP across the following time points. Okay, so we can consult the documentation to show what kind of parameters we can set here: times, channel type, layout, and some other information. So let's try to set these times not from auto, but times is the following. So we can indicate we want to see the topo map at 100 millisecond, 200 millisecond, 300 millisecond, 400 millisecond, or 500 millisecond. All right, so we can analyze it in this way. And we have other function called plot joint. So plot joint shows us joint plot, as the name implies, of the original time series visualization plus topo map. Here also we can define these times. Let's just copy and paste here and then see. Yes. So 100 millisecond, the amplitude values of ERP, 200 milliseconds, 300 milliseconds, 400 milliseconds, and 500 milliseconds. So for example, if you delete some peak here located, so if you want to see, if you want to see where in the brain this peak is happening, again just try to find this time point and set here. So let's, instead of 400 milliseconds, try to set 370 milliseconds. Okay, so almost peak. So by just looking at this, right, topo map, we see increased amplitude of the ERP in the occipital region of the ERP. We also have some method that we can show the difference or the contrast between target and non-target ERPs. So for example, we can get the difference between target and then standard ERPs and try to visualize the joint topographic plot. Right, so what does MNE combine evoked does is that we can simply subtract target non-target amplitudes and get some contrast on the differences between two, or apply some weighting for each evoked dataset. So here, let's say this point. Okay, so first of all, what's shown here is a difference between target and non-target, and topographic image here. So we can, for example, copy and see more details of this visualization as follows. Okay, so here again across 5 different time points, what we see is spatial and temporal distribution, or spatio-temporal feature of EEG. Further, we can try to plot the difference between target and non-target as a color-coded heat map. Let's call it as heat map or some image. These are channel, indexes, time point, microvolt amplitude values. So we see the difference between two conditions, target and non-target, around this time point. This is very clear and I would say beautiful visualization that shows the difference between target and non-target. Further, we can define the regions of interest. For example, here we see all 63 channels, but we can split all those sensors according to left or right hemisphere or midline. So for that, we utilize one of the methods called as make 1020 channel selection based on the midline. Okay, and then select 3 regions of interest. So left hemisphere, all these channels, midline, all those channels located in the midline center, and right hemisphere. Here, all those channels from the first region of interest, second region of interest, and third region of interest. As you can see here, all these odd numbers coupled with these characters represent the channels from the left hemisphere of the brain. We see some interesting activity happening here. So plot image, again, allows us to group all the channels by the region of interest that you define. Left, midline, or right. So midline channels here, some of the midline channels. Those are areas where central, CZ, all those located. Also interesting, difference between target and non-target. These channels, right hemisphere, 20 channels. All right. We can also use the following function called plot compare evoked, which allows us to compare multiple conditions, 2 conditions in our case. Time evolution. Look, this is, okay, after calling this function, let me just type it. Okay. We pass standard and then target, and we select one of the channel. 13 is the location of CZ channel. And we can compare. This is target and the blue line non-target for single channel. Here we have onset of the stimuli. So visually we can observe there is a significant difference between target and non-target ERP at this channel. What about channel 17? CP1. Okay. What about channel 3? What is channel? So FC. Well, here the amplitude of target is going down and location of FC is here. We don't see much difference between 2 conditions. What about 2? 2 is F7, which is located here. What about 9? FC2. Okay, we don't see much difference between target and non-target. Yes, so this kind of analysis helps you to visually confirm the difference between target and non-target. Of course, MNE provides statistical methods, statistical tests also that you can utilize for significance tests when it comes to difference between target and non-target ERPs. Let's take a look at some other plotting function we mentioned about this target and non-target MNE object. Okay, let me zoom back and then go back here. Okay, we said that these are the plot functions that our objects are. Let me just put it here. That's all. Now, target, plot. Okay, let's take a look at the sensors. Sensors. Okay, if you do that, yeah, these are the locations of the EEG sensors that the data were collected using. So if I'm show names, let me try this. If I'm okay, yeah. So we can show the names of the channels. Well, this again another helpful plotting function that allows you to quickly visualize the location of channels, okay, and the data that were collected. What else do we have? Plot, topo map, topo. Topo map. Let's try plot topo. Plot 2D topography of evoked responses. So plot top allows you to plot time series representation of ERP on the space. Look, these are the location of channels. This one is CZ most likely. And we can define what we are seeing here is ERP data on these locations, on EEG channel locations, ERP data. All right, we have seen some of the capabilities of the MNE visualization functions or method useful for target or non-target ERP, or general for many EEG object, EEG data. Now the question is, can we visualize the EEG? Can we visualize EEG using the matplotlib? So first, yes, the answer is, so first let's get the data out as an NumPy. This is our target average from epochs. Let's just NumPy and then to the import matplotlib. Yeah. So can we visualize this using the matplotlib? For that we may need to define the channel names. We just get from target info channel names. Okay, if you run this, all right, so these are the channels available. Enable scrolling. Next step is, let's try to write down a piece of code that will allow us to map from index to these following channel names. Channel, for example, C4. Okay, let's write down this to map from channel labels to NumPy indices. And then basically we can plot it using matplotlib x. Okay, 0. And then all plot title channel. Y label is amplitude. Is time samples. Let's try. Okay, here we have the example data from C4 channel. Okay, if you want CZ, okay, here data from CZ. Let's say F1. F1. Is it changing? Yeah, it is. So basically you can get the NumPy array out from the MNE object and then use matplotlib's visualization tool to visualize. Yeah, or let's visualize all data superimposed. Okay, here. So all the data in our NumPy array. Now let's take a look at the time frequency analysis methods of the MNE. For example, power spectral density, right? We have seen that as visualizing the power spectral density of EEG. So we first read the data that we have segmented with a longer duration. So oddball long epoch, this is epoch, and then just like we did before, plot power spectral density. Call it, so some parameters, this function allows us to perform power spectral density and then visualize. F min, F max, so frequency minimum, maximum frequency range, from which times period, min, max, and some other information. So plot the power spectral density across all channels. Okay, now let's define the minimum and maximum frequency range to be from 2 Hz and 20 Hz, from 2 to 20 Hz, and then try to visualize. This part, y-axis, show the decibels, okay, and x shows a Hertz frequency. These are the channels from all 63 channels, okay, the power spectral channel specific power spectral density data. Most of the useful information in EEG is located between, let's say, 0 and 40 Hertz. Yes, so we can see from 0 to 40. Okay, so this is a typical power spectral density of EEG channels. Why do we see this line here? And why the power spectral density goes down after this 20 Hz? One of the reasons is that we did bandpass. We applied bandpass filter for our data. Let me type here. So that pre-processing related information is stored in epochs and then .info here. High pass, low pass. We did perform high pass and low pass. Therefore, in the power spectral density, we can see those. Okay, cutoff frequency and effects of the bandpass filter. What about the time and frequency change of the, let's say, oddball effect? The power spectral density of the Fourier transform underlying this doesn't show us the time information. We only have frequency and then the power, right? So there is a method called wavelet transformation that allows us to decompose the signal into time and then frequency evolution, time-frequency decomposition. The time-frequency module of MNE contains many methods that allows you to perform time-frequency analysis on EEG and MEG. For example, we can try to take a look. So this is method Fourier, Morlet, multi-taper, Fourier, Morlet. So different methods, as you can see. The inverse Fourier transform, Morlet, Welsh method, multi-taper, power spectral density, and time frequency array Morlet. Different versions. Okay, so this is our Morlet, time frequency Morlet that we want to use, which computes the time frequency representation using Morlet wavelets. So wavelets is again a method that allows us to decompose time series into time and frequency representation. Let's see. So we'll have to define some parameters like a frequency range from 3 to 30 and pass our ERP target and standard and get an object called time frequency target. Okay, now we have data. Let's take a look. Shape. Yes, so the shape of the data is now different. 63 channels, 221 time samples, and this is the frequency range. Okay, we can try to visualize as follows. So let me first see if we can visualize it like plot. Okay, just plot. Let's try to plot. So frequency and time from FP1 channel. Okay. How can we define the channel name? Yeah, the channels include slices and baseline. So yeah, we can visualize different channels. So now let's again use a combined evoke, then subtract, standard, and target. This is three-dimensional NumPy array, and apply some baseline correction. Then visualize. Right, then we can see some clear pattern. Time and frequency. This information provides us where in time and then frequency we have significant difference between two different conditions. Target ERP, non-target ERP. So this red represents the difference. And in space we can see the channel following channel. And also at hertz, 4 hertz. Okay, just a moment. So we can select one channel and visualize. So OZ 13 CZ. So it provides us again time and frequency information. All right. Let me try to do this. Yeah. So time frequency analysis is an integral part of any EEG or MEG research. Using these tools, we decompose EEG into, again, time frequency representation or power spectral representation. And what we are looking for is to find some differences related to experimental conditions, right, and then underlying mental state. While in the case of PCI, this information, these kind of features, can be constructed for improved classification. You should have studied power spectral density or Fourier transforms in your signals and systems course. There are different other methods that we can use for time frequency analysis using the MNE time frequency module, okay? And you can try to find relevant documentation. Cross-spectral density, for example, using Morlet. So we have seen today how different ways we can visualize the data, ERP data, using the MNE's available methods. And we have also seen the time frequency decomposition. Please study the toolbox yourself, get more hands-on experiences. In the coming sessions, we're going to extract those data and then feed it to our classifier. I think that's it for today. I'll see you around.